just perhaps we can open up the discussion. And so first of all, I think there was one talk that we didn't have a chance to take any questions. That was Golan on pulsar timing arrays. So are there any questions for Golan, perhaps? Golan, are you still with us? Yeah, he's here. So, but I think so in terms to just put all the today's talks in the context of thinking about the Argos requirements. I think one thing that was clear to me is that we should really aim for this at least SK1 meets total collecting area that will be very useful for following up on the SKA discoveries. And this daily timing, or at least high cadence timing, is useful for a number of things, from pulsar timing array science to understanding the pulsar population. And it's not completely clear to me what would be the best engineering approach to achieve that. So I think what Aris mentioned about, this obvious thing of, if you have a very wide field instrument, then you can, observe at least 2 or 3 pulsars at a time. That's the easy part. The challenging part would be the subarray, adding the subarray capabilities. So I'd just like to basically ask everyone what your thoughts are about that, and how critical would that be for allowing us to follow up on this huge population of pulsars that will come out of the SPA servers. So Ari, yeah, you can speak up.
So one thing to say about that is, one way to think about it is to try and match these instruments. And I'll say these instruments, right? Because I actually think that Argos and others are needed in order for SK to be doing what it's supposed to be doing. But so I think that the best way to look at this is to look at, if you're matching the sensitivity, then you should match the subarray capabilities, because those two things go together. So, the SKA is going to do some pulsar timing of the, promising newly discovered pulsars. And in order to do that, it's going to have to do some subarraying to manage the time. So it will already divide its sensitivity in some reasonable way to manage that population. And in some ways, the 0th order answer to your question is copy that.
Yeah, that's I think that answers my question. So another very interesting thing that we discussed earlier is this, regarding the follow-up of LIGO transients and the possible relation of to fast radio bursts. So I wonder if people have anything to say about that. So, for instance, I wonder, how many, is there an easy way to estimate how many of these mergers that LIGO will see in the next few years will be detectable by things like the Argos Pathfinder, Argos, or any of the other instruments that will be online by then. So that's probably a nice exercise to do. not sure if, okay, so Antonis is offline, so we can probably do this discussion in the Slack.
Yeah, but I have a question, but I'm not sure if people online can hear.
I can probably repeat the question.
So what are the thoughts regarding how you do target of opportunity? Is the idea to have a sort of semi-automatic scheduling for Argos? Because, yeah, so would it be possible to trigger it in your usual way?
Yeah, so the question is if there's going to be any target of opportunity capabilities for Argos. So the answer is yes. And we are actually one of the subsystems that we're building, within the context of this design study is regarding target of opportunity triggers. So we want to be able to both generate triggers and also to receive and respond to triggers. And one of the plans for testing that with the Pathfinder is doing some sort of combined synergy with the instrument that I mentioned in my talk. So this turbo instrument that will be doing follow-up of LIGO and service, and also we also want to be able to respond to that. So one of the important things for us to think about and consider is how fast do we actually have to respond to be able to say something useful about things like FRB and double neutron star measure association, or anything else about supernovae, gamma rays. So that's one of the key specs that we want to really narrow down.
Okay, great. I've got another question that shows even more ignorance of Argos. I apologize for that. So you showed a couple of solutions for antennas that they are off the shelves, you say, apart from one of them that would be more custom. So I understand that they are not, they could be general purpose, not necessarily on the off-the-shelf one. They could be also not necessarily astronomical, they could be, right? General purpose receivers. So,
yeah.
What is the performance? So then if you need to point them in the astronomical way, right, you need to be kept especially don't they? What was their performance in pointing and zooming and stuff like that?
So I think, yeah, so I think, so let me just first repeat the question so to make sure that people, so the question was about the pointing capabilities of this off-the-shelf component, antennas that we consider for the Pathfinder and also for the full array, if they are able to actually use for astronomical.
But I don't know that, but I think the performance in getting the array to point here and there is one of the things that matters for how fast can you trigger, right?
Sure,
so
sure,
is,
yes.
You cannot do better than the antenna, so that was
well, actually, the first stage was that we were going to use some manual mounts, so no motors at all. But then we decided to have mounts that can slew. The one option that the company from Crete was offered from Megatron said that they can do motorized stuff. But actually, we didn't discuss about the fastest slew rate that the mount had. We discussed about the sidereal tracking, and what I discussed with them that is that you can do, for example, can you do for us like to have another second of slew rate, and they said that is very easy for us. In my opinion, it's a little bit weird because it's a very large instrument to have this kind of slew rate. Even if it's if it can slew with like a sidereal drive with 5 argchecks, it's not for one. It's not a problem. As the one argcheck is for the whole array. So yes, of course, the fastest skew rate that we can do, the better. So we can skew the disks to the point that we need to when there is a trigger.
So yeah, so if I may add to that a bit, I think so regarding the off-the-shelf components, most relevant to Pulsar, I think all these dishes are basically built for satellite sightings.
Yes.
So they, in principle, they can track things that move very fast. So the local company is at least one of the one of these vendors should be able to build something that can respond to move to any part of the sky from any other part of the sky within a few tenths of seconds. But that is definitely something that we need to consider more carefully in the near future.
Okay, great, thanks.
Is there any other thoughts or comments from the people online? So if not, I think we can conclude today's.
Sorry,
Sure,
can I
yes.
ask something to well, I wanted to make a comment on the subarray, but I think Alice will comment back.
Okay, so may I make a suggestion to just quickly move here for the question? Because should make it a bit more interactive, I think.
Yes.
Okay. Okay.
Right.
So the microphone is there. So you can...
I see it. Okay, thanks. So about the subarray, this question of the subarray, my view over the subarray for all science cases, so I'm not talking about pulsar specifically, is a way to maximize the efficiency, essentially, of your array, because you could do multiple things at the same time, right? And so, for example, in this sense, you could have a part of the array to look at the pulsar and another part of the array to look at the pulsar at the same time. And so the science productivity of your array improves. It added extra complexity. It adds extra complexity on your correlator. It adds extra complexity. And so I'm sure it also adds cost. I haven't worked it out. I think and this is where Aris can challenge me, because I'm not exactly sure of this, but I think you could do all that you can do with the subarrays, you could do without, but it would be less efficient. So, for example, if I have an object for which the best configuration is only to use some of the antennas, you can always do it, and the other antennas are not going to do much during that observation. So, in this, you waste part of the antennas for a bit. So I think it's indeed your efficiency of observation that it is impacted, but I think you could do without. Yes, so this I think is the two things that you need to trade off if you need to consider your design. Now, if people think this is wrong, please correct me.
I don't know if Aris wants to say something, but I think I also have the same sort of wonder about the same thing, whether if it's actually better to, at least for pulsars, to spend less time with, use the full array to spend less time on one particular pulsar, and then move the entire array to observe the next pulsar, whether that would be more cost efficient over the entire life cycle of the instead of subarraying and adding this.
Yeah, so I'm not a pulsar expert. This is why I want to venture into that. But you know, in principle, for some pulsar observation, you really don't need a full array. So even if you add the full array, it's not gonna add improve your observation as much. Let's say. So in a sense, this is why it can make sense to be able on occasion to split the array. The only thing that I'm saying is that I don't think it is a strict requirement that in order to do the pulsar well, you need to subarray, but then you would have either you point your roll antenna and then, you know, some of the data are not really anti-match, or you have a part of your, for some observation, you have part of your array idling. So it is a bit less productive, if you like. So yeah, you need to balance with the increased complexity of everything that you have with the subarray, which there is some other complexity. We cannot pretend that that is not.
I think the subarray for bright pulsars is very important, because otherwise you can do all of the brighter pulsars at this, well, in much smaller amount of time. Because I mean, if you spend a minute observing a pulsar, you're not going to get a good flux from that, or even a good pulse profile because of jitter. So I think it's for many average properties like pulse profiles, polarization, and so on, you might want to have lower sensitivity, but to observe for longer, because they have more pulses. So anyway.
Yeah. Okay, I think Wei had a comment as well.
In the perspective of the backend, we can so in Meerkat we do this broadcast and subscribe mode. So the backend will broadcast all the data, either the calculating data, and then you can have multiple different servers, GPU servers or CPU servers do different things. One will do pulsar search and also timing, or the other can for images. It's just subscribing the data stream from the backend. So that's what they do in the Meerkat. They have multiple clients with different projects to share the same the data from the same observations.
And so Golam is also saying something in the comment section. So would it matter if the subarray did only software beaming instead of pointing parts of the array? So you only observe it in relatively close areas, but still can cover a range of sources. So Golam, can you please? I'm not sure I understand the comment.
Yeah, sorry if there's some background noise. So basically, in LoFa 2.0, what we often do is when we're looking at solar transients, we also keep a beam on a pulsar, because the pulsar can give us, if we're really lucky, it can give us both TM and RM. Hasn't really worked out very well so far, but I imagine with something like Argos, which is at a higher frequency and has enough bandwidth, you could actually do something like this. But the thing is, you're not physically pointing your array in LoFa. It's just a software switch that is adding up phases in different ways, which is all on a computer. So it's a lot cheaper. It's a lot easier to implement in some sense. But if you're at higher frequencies, you don't have to worry about a lot of the things we do at LoFa. So it's something of this sort, where you're not physically moving dishes, but you are adding up the beams in different ways.
So I think, yeah, so R is logged out, so that's probably why he didn't comment. So I think we can also continue this discussion in the Slack with him. But that's certainly very critical thing. there anything else that you guys would like to discuss today? I mean, we can always continue the discussion. If not, I think we can yeah, we can close today's session.
So
thank.
my talk to tomorrow.
Oh, there's one more talk. Sorry, Sam. I completely screwed up today. So.
That's right. But you want to do it now, or?
Yeah. Please go ahead. So sorry, everyone. There's one more talk before we. So.
That's all right. I'll be quick. Okay, so should I share my screen on?
Yeah, please.
Yep.
No, you should disconnect from Zoom.
Okay.
And use the HDMI there to connect. I think that will make things easier.
Okay. To do something. All right. I think everyone's probably pretty tired, so I will try to go fairly quickly. Just to make it easy for everyone, the takeaway from this talk I'm going to give you already at the beginning, so that it's pretty easy to follow what the point of the talk is. So what I'm just trying to do today is give you a quick overview of who's working on machine learning stuff for Argos, what some of the stuff we've done in the past and how this relates to things that we will be doing for Argos. And then I will kind of focus on one particular project that we're going to be kind of resuming now that we have some manpower to actually continue. Just kind of give an overview. So effectively, this activity for Argos is just getting started now. So there's no, exciting results to share with you at this stage, but there's a lot of exciting potential. So that's what I want you to focus on. Okay. So, my name is Sam. I work at the CA, which is the French Alternative Energy and Atomic Energy Commission. So if you're not familiar, this is Paris, and the little dot there is Saclay, which is where the CA is located. The CA employs somewhere around 10,000 people to work on almost everything you could possibly imagine. Our group is called Cosmostat. We're based in the astrophysics department at CA. Our particular interests are things like signal processing, machine learning, and cosmology, and in particular using state-of-the-art methodology to solve problems for cosmological analysis. Okay, so some particular projects that we're working on in Cosmostat are Euclid. So this is a space telescope that was launched this year in July. It was very exciting. So this is launched by ESA, which is going to be mapping the dark matter distribution of the universe, basically designed to give the most precise measurement of the shape of galaxies to date. But we're also involved in some ground-based surveys like the Varese-Rubin Observatory and a project called Unions, which is going to be providing ground-based photometry for Euclid, but we're also using that for doing some cosmological analysis. So then finally, and obviously the most related to Argos, is that we're starting to dip our toes into SKA as well. Okay, so just to give you a little story of what we're doing in Cosmostat that is not directly related to Argos, but still interesting. So one of the primary focuses we have is gravitational lensing. So for those of you maybe not familiar, this is when some background source, like a galaxy, gets the path of its light distorted by some foreground dark matter distribution, which in turn, lenses that object, and by a very small amount, so you get a very small distortion. And so, in an indirect way, by measuring the shapes of galaxies to high precision and statistically across the whole sky, we can then produce a map of the total dark matter distribution of the universe. Right? So effectively, the more accurately we can get the shapes of galaxies, the more accurately we can understand how much dark matter there is. So one of the things that we've done is develop a shape measurement pipeline. So we go right from raw images all the way down to cosmological analysis. But each one of the steps involved in this process are in itself very complicated and very painstaking, and involve a lot of things like signal processing and machine learning to help us solve different aspects of this. So one aspect in particular is the estimation of the point spread function of the telescope. So I'm going to come back to that point in a little bit, and this will relate onto a talk that you're going to hear on Friday. But if anything I talk about in the next few minutes is interesting to you, I would highly recommend that you go check out our website. So on Cosmostat, you'll find about all the projects we're working on, all the people that are working on the projects, and how to get in touch with people, and so on and so forth. Also, you can find us on Twitter or X now, and all of the software that we produce in the lab is also freely open source on GitHub. Okay, so who's working on Argos in Cosmostat? So we have Jean-Luc Stark, who's the head of the lab, and also one of the kind of big names in astrostatistics. Signal processing was kind of one of the pioneers in the use of wavelets for astronomical data analysis. There's myself, and Ezekiel, who's seated right across the room, who just started his PhD this month, and he's going to be giving you a talk on Friday about the work that he did during his master's. And this, again, will relate back to that PSF point that I mentioned earlier. So in addition to that, there's two other staff members in Cosmostat that will be kind of, in a more consulting mode for work that we're doing on Argos. So we have Martin Kilbinger, who's an observational cosmologist, and Francois Lanous, who is an astrostatistician, but also one of the world leading experts on machine learning for astrophysics. So we did have another staff member who has just recently left the lab because she got a very nice job at ESA. So she will no longer be involved in Argos activities, sadly. But we do have good news in that we will have another PhD student joining the lab shortly to work on Argos as well. Okay, so in the aspect of signal processing for Argos, we will have to work closely with the fourth computer science group here. We're also going to be doing similar sort of things. So we want to interface closely with them to make sure that we have good overlap and diversity of subjects that we're handling for Argos. Of course, we'll be interfacing with the other teams as well, but I think in the context of this work package, that's the obvious team to relate to. The specific tasks that we need to handle for Argos in our group is the 2D and 3D image reconstruction of radio data, the use of machine learning or neural networks in particular to handle that reconstruction, and the detection of transient sources. So I will come back to those points in just a few minutes. Firstly, I'm just going to give you a little bit of background of some of the things that we've done in the lab. The approaches that we've taken to handling certain things, how those can kind of tie into what we're going to be doing for Argos, and how we're trying to build from that into going forward. So, just a quick hands up is how many people in the room have heard the term inverse problem in their day-to-day work? Okay, so just a few. So, just to kind of answer that question in case you were wondering what is an inverse problem, right? The traditional definition would be, assuming that you have some cause, you go from your cause to the effect would be called a direct problem, and therefore, conversely, going from the effects to find out the cause would be an inverse problem. But in a more practical sense for astronomical applications, we could replace those words with model and data, right? So when we're trying to infer an underlying model to some problem we're trying to solve from the data is essentially what we would call an inverse problem. So, we can model inverse problems using linear algebraic formalisms like this, where we have some, data that we observe. We have some operational matrix that, degrades that data or masks that data or does something to that data that, that we want to essentially combat. And then we have the underlying model or, essentially true data that we want to recover, and then some, component of noise that we have to account for. right? So just to give you a concrete example of what kind of problem we're trying to solve with like this, a formalism like this would be something like deconvolution. So imagine that we have some observed image that we've taken. I mean, presumably in most applications, it's not going to be a raccoon, but it could be a raccoon. We have some observational matrix. So again, this could be something like the point spread function of your instrument. If we were talking in radio, this would be the mask of the visibility space that you're dealing with. And then what we want to uncover would be the deconvolved image, or the nice recovered image pixel space. Right, so the thing is that this looks very simple, mathematically speaking, that if you were just to invert this H matrix, you should be able to recover your original image. But of course, with this noise term, that destroys everything in the signal, right? Because you get this high frequency component from the noise that essentially invalidates a direct inversion of your matrix. So what instead you need to do is look at this in terms of what's called an ill-posed problem, right? Where essentially the matrix that we're dealing with here is ill-conditioned, which means that it's a nonlinear effect of changes in this operational matrix to the data that we observe. And this is exactly what you get from a point spread function. So how do you handle something like this? As well, you use what we call regularization, right? Essentially, if you were a Bayesian, what we would call it is a prior. If you're a signal processing person, you call it regularization. And if you're in machine learning, you call it, I don't know, your architecture for your network. Effectively, what this is doing is giving us some prior knowledge on the problem we're trying to solve. So for a very, very basic example, if we were to deal with something like a sine wave, we know inherently that if you would take the Fourier transform of a sine wave, that decomposes into something very simple with a single frequency component. So if I know that this is a true attribute of the signal I'm trying to recover, I can impose that any solution that I get from the data that I'm trying to resolve has this attribute as well. Reduces the possible solutions that I can get to the problem, and then also helps me, get a good solution overall. Right, so I can, mathematically implement this in the following way. So I have some data fidelity term here, where I want to try to, from my observed data, recover my true underlying signal to good quality, but also conditioned on that it has this regularization property. Obviously, in this very simple example would be for a transform, but it could be, of course, a more complex wavelet basis. It could also be a really complex basis that we learn through machine learning, right? Essentially, some fundamental, non-obvious latent property of the signal that we're trying to recover. Okay. So again, if you were a Bayesian person, this would just be a very informative prior that you are very confident of. Okay, so some ways that we've used this type of methodology for practical applications. One of them was a project that we had in collaboration with a biomedical imaging group at the CA called NeuroSpin, where we worked together to develop a piece of software called PySap, which stands for Python Sparse Data Analysis Package, which is essentially a toolbox for solving linear inverse problems using sparsity as a regularization variable. And what we've been able to do with that is things like galaxy image deconvolution, right? So effectively the same problem I was showing you before, slightly more complicated mathematical framework for explaining exactly the same thing. But essentially right here, what we do is just have a sparse prior on the data we're trying to recover. But we've also